Hi, today we're going to be looking at supernovae, supernovas. Supernovas come in different flavors, and the ones we're going to be looking at today are created as a result of a high mass star and the consequences of trying to fuse iron. So that's what we're going to be looking at today. So in our last podcast, we got up to this point, and we talked about silicon burning day, which is the single day at which a very high mass star, greater than 8 solar masses, is able to fuse silicon. So it ends up with this kind of onion shell arrangement of an inert iron core sitting at the middle, and then nested shells of all the different elements of fusion: silicon, magnesium, neon, oxygen, carbon, helium, and hydrogen, all of which exist in the core. And then above the core, to remind you of this red supergiant stage, there is a vast, vast, vast envelope of non-burning hydrogen that can extend as far as 1,000 astronomical units. So during this single day, an iron core builds up, and in one day it will build up to about 1.2 to 2 solar masses. It begins to contract, it begins to heat up, and then finally it collapses. There are two processes which aid the fact. The basic fact is that if you try to fuse iron, to create energy, you're going to have a bad time. The binding energy per nucleon of iron is the highest of all of the elements. It is impossible to fuse iron to get energy. Additionally, you've got some incredibly high energy photons flashing around that heat up the nuclei and turn them into a proton, neutron, helium soup, in effect undoing the fusion, absorbing these photons, which takes energy away. In addition, protons and electrons from this soup will recombine to form neutrons. That takes in energy. The process creates a lot of neutrinos. The neutrinos take away energy. So previously, where you had this incredible engine of energy production in the core, it stops happening. It ceases functioning. Every star is built around the concept of hydrostatic equilibrium. Gravity is pulling in, and there has to be something opposing it. And when the iron core collapses, there is nothing opposing gravity. Gravity wins. So what happens? Well, our core goes from a radius of about 6,000 kilometers to a density of about 10 to 11 kilograms per meter cubed, down to a radius of about 50 kilometers and a density of about 10 to the 17 kilograms per meter cubed in 1 second. That means that the speed of that collapsing core is about 0.25 times the speed of light. With kinetic energy being K equals a half mvc squared, this is a very significant amount of energy that is being released. That core collapse continues until that density is about 2.4 times 10 to the 17 kilogram meters, at which point it halts and it rebounds. Now the rest of the star is also collapsing around the core, but it's not quite so fast, and so the infalling gas hits the bouncing core. This creates an insane shockwave with a kinetic energy of about 10 to the 44 joules. This expands outwards for 24 to 40 milliseconds until the infalling gas equals the mass of the outgoing shockwave, and the shockwave briefly stalls, stops pushing forwards, but the immense numbers of neutrinos that are flooding out. Now, neutrinos hardly ever interact with normal matter, but they're interacting in such vast numbers that they heat and drive huge convection currents in the envelope, which breaks up the shockwave. So the shockwave resumes after about 300 milliseconds. The incredible pressures and densities along the shockwave create nuclear fusion of heavier elements, so large numbers of elements greater than iron are produced. They heat and accelerate the stellar envelope. Now, it takes a while for this shockwave to break out of the stellar envelope because, as I previously said, the stellar envelope is so large, up to 1,000 astronomical units. But eventually it does after a few hours, and at the time it does, it's still traveling the shockwave at about 10% of the speed of light and has a huge amount of energy. Seen from a distance, Here we have what we believe to be about a 15 solar mass blue supergiant, which went bang in 1987 and produced the brightest, most recent supernova that was visible to the naked eye if you lived in the southern hemisphere. So this is the before picture on the right, and here is the after picture on the left. Here is another supernova which we observed in a galaxy in the year 2013. And on the left you can see a picture of a galaxy pre-supernova, a relatively distant galaxy, and on the right is the same galaxy with that nova. So that star has brightened to a luminosity of about 10 billion times the luminosity of our Sun. It's producing more output than an entire galaxy. It produces more energy than our Sun will produce in its entire 10 to 11 billion year lifespan. The envelope is blasted off into space and only the core remains. Over a period of weeks or months, the star fades. It still glows by the leftover heat of that event, particularly driven by some of the radioactive isotopes, particularly nickel, that are produced, and they give energy through gamma rays to the surrounding material. The light curve is characteristic. As I said at the start of this presentation, there are different types of supernova with slightly different processes, and you can recognize the different types from the light curve that they produce. The remaining stellar remnant, the remaining envelope, is pushed off and mixes into the surrounding interstellar medium, which is important for the whole life cycle, emphasis on cycle of stars, because those heavy elements it produces are mixed up. This photograph is actually from that 1987 supernova explosion, and this is what it looked like much more recently. On the left you can see an overall picture taken a few years ago, and you can see a couple of lobes of the outgoing shock wave, and in the inner stellar remnant here. Now, in the early photographs from the early 90s, this actually, the surrounding ring already existed. It was the result of a thermal pulse in the star before it exploded as a supernova. You might remember we talked about those. But then in the later picture, starting from about 2003 onwards, you see it suddenly gets a lot brighter, and that's the result of the shock wave, the expanding shock wave from the 1987 explosion, slamming into this pre-existing gas envelope, gas shell, and heating it and making it glow. So that's the emission nebula that remains. What remains to the core is what we'll look at in the next podcast.